Here we go. Long division. Okay, so we're gonna long divide polynomials today. But before we review before we do long division of polynomials, we need to review long division of numbers. So let's look at this right here. If I say what is 277 divided by 12, that could be a problem that you had sixth grade elementary school even, right? What's 277 divided by 12? Well, what would you do? You would set up your division box like we see on the right. You would put the 277 on the inside, and you put the 12 on the outside. The inside, or the first number, is called the dividend, and the second number is called the divisor. Okay? And the result is called the quotient. Right? So the dividend goes on the inside, that's your first number, divided by the divisor, and you get the quotient. So remember, if it's a two-digit number, you're like, ooh, that's two digits. 12 doesn't go into 2, so you can put a 0 here. But then you look at the next number, 27. 12 goes into 27 twice. And you multiply then, don't you? 2 times 12 is 24. And then what do you do here? You subtract. There's no minus sign showing there. I'll add one. You subtract after you multiply. And you end up with 3. And then you bring down the 7. Yes, yes? Okay, once you bring down the 7, you then say, how many times does 12 go into 37? And you say it goes in 3 times without going over. And then you multiply and you get 36, and you subtract and you get 1. Now, at some point, you learned that you could put a decimal and you could keep adding zeros, right? And you can get decimals. But before you even learn to keep going and add decimals, you would get to the 1 and you would say there's nothing else to bring down. Does 12 go into 1? 12 does not go into 1. So we called that number the what? The remainder. We called that the remainder. And then you could write this, 277 divided by 12 is equal to 23 plus the remainder, 1 divided by 12. Bless you. That's how you could write it. 23, it goes in 23 full times plus 1 left over out of the original 12. Okay? You probably even got rid of the plus sign and wrote it as a mixed number, didn't you? And you read that as and, 23 and 1/12. It's the same thing. Okay? Now, that's what we're going to do today. 27 divided by 12 could actually be, or 277 divided by 12 could actually be written like that now, can't it? Y'all know that if we write a fraction, 277 over 12, that horizontal bar right there means to divide. So they mean the exact same thing. So today what we're going to do with polynomials is we're going to learn how to take something that looks like that, 277 over 12, and we're going to write it as 23 plus 1/12. Okay? And this is the form that we're going to do. The dividend over the divisor is equal to the quotient plus the remainder over the original divisor. That's the form of the number that we're going to be using, or for polynomials, okay? That's it. It goes in this many full times, plus that left over out of the original. Okay, let's take a look at the process is the same, we just have variables that we're carrying around. Let's try this right here. We have a third degree, a cubic, 4-term polynomial, divided by a quadratic trinomial. Divided by. All right, so the first thing I'm going to do is I'm going to write it in the other format. 4x cubed plus 2x squared plus 3x plus 5 divided by, I'm going to write it as over x squared plus 3x plus 1. Those two things mean the exact same thing, don't they? Good morning. Those mean the same thing? Yeah, okay. Now, to perform the actual division, like we did up here with the numbers, we're going to create this right here. I don't know what you call this. Maybe your teacher called it the horse and the rider back in the day. Did y'all have a little silly name for that? The horse in the stable, the rider in the stable, the 4 horsemen of the apocalypse. What did they call that? The horse and the cowboy. Okay, that makes sense. We're going to do the horse and the cowboy for polynomials. So which one goes on the inside? The cubic or the quadratic? The cubic, right? The first one, or the numerator, that's called your what-a-den. Do you remember? Dividend. Good, y'all remember the terminology. So the dividend goes on the inside. And I'm doing this off to the side, by the way. And we write the stable, or the horse. What was that? An arrow, what was that? What did you call that line? Was that the horse itself? Or was that the stable? The stable? Okay. And then out front, we put the x squared plus 3x plus 1. That's called your what? Your divisor. Sehr gut. All right, so here's how we to do the long division of polynomials. We're going to focus not all three terms and all four terms. We're going to focus on the first term in each of them first, right? It's kind of like divide and conquer. And we're going to do the division. How many times does x squared go into 4x cubed? Like up here, we asked ourselves that question. How many times did 12 go into 27? It went in what? It went in twice, okay? How many times does x squared go into 4x cubed? Right? That's kind of a silly question. Once? A half a time? Well, here's what we're actually doing. Let's come off to the side here. What we're actually doing is we're doing 4x cubed divided by x squared. That's actually what we're doing. We're doing the division with the first terms only. Now, when I write it like that, that makes it a little bit easier to work with, doesn't it? What does this simplify to? 4x, doesn't it? Because the x cubed and the x squared divide out to give you x. So there, that's 4x. So that's the answer. That's the answer. How many times does x squared go into 4x cubed? 4x times. 4x times. Okay? So feel free to go off to the side on your workbench. Remember, you got unlimited space over here, and actually do the division and simplify and bring that up into your quotient. All right, what was the next thing we did up here when we said it went in twice? What do we do with the 2? We multiply, didn't we? We're going to do the same thing. We are now going to multiply. We're going to multiply the 4x by the entire divisor, which means we're going to have to do what? Distribute. We're going to have to distribute. So let's go ahead and do that one term at a time. We're going to write the result underneath the dividend. So what's 4x times x squared? 4x cubed. We're going to write that underneath the other cube term. Now, here's a checkpoint. If you did your quotient right, those two right there that you're stacking in the first column, they should be the same. If they're not the same, you have to go back and do the first step more correctly. All right. Now, what is 4x times 3x? 12x squared. I'm going to write the 12x squared underneath the squared term that's there. And it's a positive 12x squared. And then what's 4x times 1? Plus 4x. Good. So I distributed it all the way through, and now I'm going to draw the line. What did we do up here after we multiplied? I subtracted, right? I subtracted. That was a good sound. Can you do that again, Anera? I like that. That's the kind of sound we like to bottle as teachers. All right. Now, be careful here. When you're subtracting a polynomial, which means you're going to have to subtract each term. So instead of putting a negative up front with parentheses, which can get kind of confusing because you're subtracting, here's what I recommend. When you're subtracting, change all the signs. It's like distributing the negative. Change all the signs. So I'm going to have a negative 4x cubed, a negative 12x squared, and a negative 4x. And then all you have to do is add vertically, which is easier. All right, now, what's 4x cubed minus 4x cubed? 0. You should get a 0 in that first column, or you didn't do the first step right, okay? Now let's see what we get. What's 2x squared minus 12x squared? Negative 10x squared, ooh. And then 3x minus 4x is negative x. Okay, now, let's come back up here to our template. When I subtracted before, I got 3. What did I do next to get the 7 there? Bring it on down. So guess what we're going to do next? We're going to bring down the plus 5. Seguro. There we go. Okay. And now we're going to do the exact same thing, just like we did up here with numbers. Remember, then we said how many times does 12 go into 37? You just repeat the process, okay? So let's do that. We're going to look at the first terms only again. So we're looking at the x squared and the negative 10x squared. How many times does x squared go into negative 10x squared? Not 10, but negative 10. Now, again, if you're not sure what that number is, go off to the side. It's really negative 10x squared divided by x squared. That's really what we're doing. The x squareds divide out to give you negative 10. So we go right here, negative 10. All right, what's the next step? Distribute. Now we distribute the negative 10, only the negative 10, to all three of those. Let's see what we get. Negative 10 times x squared is negative 10x squared. Are those columns the same? Those rows the same in that first column? They are. That means we did it correctly. All right, negative 10 times 3x is negative 30x. And then negative 10 times 1 is negative 10. Okay, perfect. So we distribute it all the way. I draw the line, and then what do I do next? Change all the signs. Change all the signs. So we got a plus, and a plus. If she had come a little earlier, she could have heard the story. What's negative 10x squared plus 10x squared? 0. We should get a 0 in that first column every time, or we didn't do it right. Now, what's negative x plus 30x? 29x. And what's 5 plus 10? 15. Okay. And then we just keep going until we can't go anymore. Now I have a linear function there. So we ask ourselves, does x squared go into x? No. Once you get down to the bottom and the degree is smaller than your divisor, something big like x squared can go into itself, x squared, but it can't go into anything degree smaller than x squared. So we're done. We're stuck. So guess what we call this right here? We call that the remainder. As soon as that degree, which is x to the first, gets smaller than our divisor x squared, we're done. We get our remainder. So here's what we could say. Let's bring this down here. When I wrote it as a quotient, let's write it down here. So what we could say now is 4x cubed plus 2x squared plus 3x plus 5 divided by, take a breath, x squared plus 3x plus 1 is equal to the quotient. What's our quotient? 4x minus 10, that's our quotient, plus the remainder. What's the remainder? 29x plus 15 over the original divisor, which is x squared plus 3x plus 1. And that's it. That's it. That's another way to write that rational. We call that a rational expression. It's a polynomial over a polynomial. It's equal to the line 4x minus 10 plus this little remainder piece. Now, this is important if you want to take higher level math like calculus, because when we're looking at something like this, I'm always interested in knowing what happens as x goes to infinity. In other words, what's the end behavior? We've analyzed that in here before, right? As x goes to infinity. Well, I don't know what that graph necessarily looks like locally. I don't know what the x-intercepts are. I don't know if it has local max or min, but it's pretty easy to tell what the end behavior is because of this. Watch. What happens to the remainder as x goes to infinity? Well, the top is getting bigger, but it's getting bigger linearly, like 1, 2, 3, 4, 5. The bottom is also getting bigger, right? Because it's x squared. But because it's x squared, the bottom is getting bigger faster, like 10, 100, 1,000, 10,000, 100,000. What's happening to those ratios? 1/10, 200, 3,000, 4/10,000, 500,000. Are those ratios themselves getting bigger or smaller?
Smaller.
They're getting smaller. They're actually getting smaller, approaching what? They're approaching 0. Yeah, they're approaching 0. I always like to make the analogy, think about like water and pee. Water and pee-pee, okay? Would you drink something that was 1 part pee to 10 parts water? I probably wouldn't either. Good for y'all. Would you drink something that's 2 parts pee to 100 parts water?
No.
Probably not. What about 3 parts pee to 1,000 parts water? Some of y'all are like, now you're speaking my language, right? But for some of y'all, that's still like, oh, that's still too much pee. What about 4 parts pee to 10,000 parts water? What about 5 parts pee to 100,000 parts water? What's happening to the concentration of pee in the water? It's getting smaller, right? We're diluting it. We're diluting it. And we're diluting it to a point where eventually it might be 10 parts pee to a gazillion parts water. Would you even notice the pee, essentially, in that case? I read something on the news yesterday that every single bottle of water has microplastics in it. But it's such a small concentration, they're so small, we don't even notice or taste them. But we drink it anyway, but it's so small, it's practically 0. Okay? So here's what we notice. We notice then that the remainder approaches 0 for large values of x, which means this function right here is going to start behaving more and more like 4x minus 10. What does the graph of 4x minus 10 look like? Isn't it a line that has a y-intercept of -10 and a slope of 4? Yeah. So guess what this function right here, if we call that function f of x, guess what that function looks like from space? From space, you're not going to be able to see the x-intercepts, the y-intercepts, the local max, the local mins. You're not going to see that. Guess what you're going to see from space? You're only going to see this right here. That's what the graph looks like from space. For larger and larger values of x, that function, f of x, looks more and more and more like 4x minus 10, which is that graph right there. So that's kind of an idea that extends to calculus. But I wanted to motivate you why it's important to know how to do long division. It gives us another view, another equation that gives us another view of the function itself. Okay? It gives us another view of the function itself. But that's how you do long division. It's just a process, and once you understand the process, which mirrors the long division of numbers, which hopefully everyone still remembers, it becomes pretty easy. All right. I will explain synthetic division can be used when long division must be used. All right. That's your next goal. Synthetic division. Okay. For this problem right here, there's no way to do it other than long division because we're dividing by a quadratic. But there is another way to do the division right here in a streamlined process that doesn't look as cumbersome is the word I'm looking for. This looks kind of chunky, right? There's a lot of X's and symbols in there. There's a lot of things that we write down to make it happen. It's not difficult, but it is a lot of writing. There's another process called synthetic division, which works when you're dividing by a linear binomial or a linear function. Okay, this works when you're dividing by something of the form mx plus b. Okay, it doesn't work when you're dividing by a quadratic. It doesn't work if you're dividing by a cubic. But it's called synthetic division, and it has its roots from what's called nested form, which is a programming language. Okay, let me show you what synthetic division looks like. Or let's take a look at this problem two different ways. What if I wanted to take this cubic trinomial and divide it by the linear binomial x minus 2? Well, let's go ahead and look at what the long division would look like. We don't actually have to do it. We would put 3x cubed plus 4x. Notice what did they do here? When they were writing it inside the stable or the barn, there was no x term, was there? So we put a placeholder for the x term. We put a 0x so that when we do our multiplication and we distribute, there will be a column for every power of x. So that's kind of an important thing. If you're missing powers of x, you want to put a placeholder of 0x. Okay? So let's just kind of go through this. How many times does x go into 3x cubed? It goes in 3x squared times, right? Because that's what 3x cubed divided by x is. If we distribute from on top, we get 3x squared minus 6x squared. Notice the subtractions out front with the parentheses. That's the same thing as changing both signs. So if I want to change both signs, I'll make that a negative, and now I subtract, and I get 10x squared, and I bring down the 0x. You could also bring down the plus 10 if you want. In other words, you can bring down everything as you go. That's how I like to do it, because then we're just working with this. This is our new starting place. All right, how many times does x go into 10x squared? It goes in 10x times, right? If we distribute, we get 10x squared minus 20x. Now notice, because we have a placeholder there for the 0x, I have a place to put that 20x. If I change both signs, this becomes a negative 10x squared and a positive 20x. When I add, I get positive 20x, and then I bring down the plus 10 again. And how many times does x go into 20x? Does it go? Yeah, x goes into 20x 20 times. So I do it 3 times now. Now I distribute the 20, and you get 20x minus 40. And then if you change both signs, this becomes plus. That becomes, I'm sorry, there's missing parentheses there, aren't there? There should be parentheses there. Or you change both signs, and you get minus 20x plus 40, and you get 50. Does x to the first power go into 50, a constant? No, once the x disappears, x doesn't go in. That's really technically 50x to the 0 power. That's what it technically is. So x to the first does not go into x to 0. So 50 would be our what? It would be a remainder. Yeah. So what I know that I can do then is I can write this as, let's go ahead and write it right here. We could say 3x cubed plus 4x squared plus 10 divided by x minus 2. It can be written as the quotient 3x squared plus 10x plus 20 plus the remainder, which is 50, over x minus 2. All right? Now, just to kind of go back to what I was saying, as x goes to infinity for very large values of x, the remainder goes to 0. 50 over 10, 50 over 100, 50 over a million. As the remainder goes to 0, and we're getting closer and closer to adding nothing, which means from space, the function on the left from space looks like the quadratic. It looks like a parabola, 3x squared plus 10x plus 2. If you were to view this guy from space, you would see this parabola. Parabola from space. That means if you zoom way out. Okay, now let's look at the synthetic process. I think you're going to like the synthetic process. First of all, I don't put the 2 up there. I'll show you where I put the 2. I put the line extending out here. So step 1, what we're going to do is we're going to take the coefficients. We're going to take the coefficients of our dividend, which are 3x cubed, 4x squared, 0x, and 10. We need a placeholder for anything that's missing. So we're writing it in descending order of degree. So we're just looking at the coefficients, okay? And notice we write them along the top right there. 3, 4, 0, 10. It's a lot more streamlined if you don't have to put the x's. Would you agree? So 3, leave a space. 4, leave a space. Placeholder for 0, and then a 10. So these values, they go right here. Okay, now we're going to draw a line underneath there, and we leave a row. So let me show you. If you want to get your white tool, you can white these out right here. We don't know what those numbers are just yet. We don't know what they are. So you can just leave a little blank row right there. We'll come back and fill them in. But you're going to draw a line. You're going to draw a line and leave that row. And then we don't know what those numbers are underneath there either. I'll show you what we're going to do. This is called synthetic division. Now, here's the deal. When you do synthetic division, instead of dividing by the factor, x minus 2, we're going to synthetically divide with the root, or the 0 of the factor, which is what? 2, okay? If x minus 2 is the factor, x equals 2 is the root. I put the 2 down here out front, and I put a bar on it like that. So you can put it up top like the notes have it, but I always put it down on the bottom line right there. So pretend that this isn't here. So we put a 2 out front, and we put it in like this little half of a box. We put a little line there to separate it, okay? Now here's how you do synthetic division. Step 1 is the easiest of all. You bring down the first number. So the 3 just gets brought down, and it becomes a 3 right there. That stays the same. Now here's what you do with this number. You're going to multiply along the bottom line. You're going to multiply along the bottom line with that number, the root that's in the box. So help me out. What's 2 times 3? 6. Now, what do you do with that 6? You slide it up into the next column. You slide it up into the next column, and then you're going to add. You're going to add. What's 4 plus 6? 10. So that's where that 10 comes from. And then we're going to do it again. Just like the regular process, we're going to keep doing the same thing over and over. What's 2 times 10? 20. We slide the 20 up into the next column, and then we add vertically. What's 0 plus 20? 20, right? And then we do it one more time. What's 2 times 20? 40. We slide it up, and then we add. What's 40 plus 10? 50. Okay. When we get that last number, we put a return box on it like this. We put a return box on it. So when you're setting it up, here's what it should look like. 3, 4, 0, 10. You should draw a line like this. You have a box out front like that, and then you have a box on the back end like this. That's kind of how we set it up.
Wait, where did you get the 2 from?
The 2 is the root of the divisor.
Oh, okay.
So if we're dividing by x minus 5, what would I use? 5. If I were dividing by x plus 7, what would I use? If I were dividing by x plus 7, I would use negative 7, right? It's always the opposite number. Now let's go through it again. I want to show it to you again. This would be the setup. Your coefficients in descending order, placeholder for any missing x. The 2 goes in here. We bring it down for the first step. We multiply to get 6. We add, we get 10. We multiply to get 20. We add, we get 20. We multiply, we get 40. We add, we get 50. Do you recognize that 50 from the long division process? It was the what? It was the remainder. This right here is called your remainder box. So if you're just interested in what the remainder is, you can do synthetic division, and it's a lot quicker. It's a lot cleaner. It's a lot more efficient. Now, what if you wanted to get the quotient? Remember, the quotient was 3x squared plus 10x plus 20. We did do a division process, but I only seem to have gotten the remainder. Is there a way to get the quotient, which was 3x squared plus 10x plus 20? Do you see it? Yes, you may. On the bottom row, mira. Do you see those numbers in front of the remainder box on the bottom row? 3, 10, 20. What was our remainder again, or the quotient? 3x squared plus 10x plus 20. Nombre, simbre. It works that way. Those numbers down there, I'm just going to get rid of that again. These are your coefficients of the quotient, which remember is going to be 1 degree smaller. It's 1 degree smaller than the dividend. Okay, so because we started with an x cubed, those are the coefficients starting with x squared. So you can actually do division by a linear factor synthetically, and it saves a lot actually. It's a very, very quick, efficient process. All right, but it has some drawbacks. You have to only do it with a linear root or linear factor, and of course you need a placeholder for any missing x in descending order degree. But you can get the remainder and you can get the quotient. All right, let's try it out. You ready to try it out? All right, let's try out. It says, given a polynomial, use synthetic division. All right, so I don't think we need to go through long division again. I think you got that. But I want to do this divided by x plus 5. First of all, my divisor is x plus 5. Is that linear? Yeah, this is a linear divisor. So that means I can do synthetic division. Yay. So what am I going to do for synthetic division? I'm going to take my dividend, which is the first thing listed, and I'm going to write the coefficients in descending order, and I'm going to put a placeholder for any x term that might be missing. So the first number I put is a 2. What goes next? 9. What goes next? 0. Very good. There is no x squared term, is there? So you put a 0. What goes next? 22, and then -8. Now, how much space do you leave in between your numbers? That's up to you. Just a comfortable amount, just to make a column. All right. Now, to set it up, we draw a horizontal line underneath it with enough room for another row, and I extend that line out past the 2, and I put a little box here on the front end, and then underneath the last number, I put a return box on the back end. That's the setup for synthetic division. Okay, now let's do it. What number goes into the box out front if we're dividing by x plus 5? -5. Good. This is the root of the factor. -5. Step 1 is easy, right? Step 1 is bring down the first number. It kind of primes the pump, if you will. All right, now what do? I multiply, right? What's -5 times 2? -10. I'm just going to slide that into the next column. What do I do in the columns now? I add. What's 9 minus 10? -1. I multiply. What's -5 times -1? I multiply. Yeah, I multiply. Yeah. So I get 5, and I slide it up in the column. I add the columns. What's 0 plus 5? 5. Okay, good. Now I multiply again. What's -5 times 5? -25, and then I add 22 minus 25. -3, and then I multiply again, which is 15, and then I add, which is 7. 7 is our what? remainder. Does that polynomial x plus 5 go into the other one evenly? No. What would we be looking for in the remainder if it went in evenly? A 0, right? Just like if a number goes into another number and the remainder is 0, it means it goes in evenly, and we would call that divisor not just the divisor, but we would call it a what? If the remainder is 0, we call it a what? Like if I do 25 divided by 5, it goes in 5 times, the remainder is 0. I say that 5 is not only, this is not only a divisor, it's a what? A factor. Very good. Yeah, it's a factor. So if your remainder is 0, your divisor is a factor. We got a remainder of 7, so x plus 5 is not a factor, but we can still write the division as the quotient plus the remainder. So here's what we can say. We can now say that 2x to the fourth plus 9x to the third plus 22x divided by 8, or minus 8, sorry, all divided by x plus 5. That could be a function in and of itself. I could graph that on my calculator. It's going to equal what? What is the quotient? 2x to the what power? Cubed. It's 1 degree smaller. And then what's the next term? Negative 1x squared plus 5x minus 3. Where did those numbers come from? Not France, but the bottom row, yeah? The bottom row. That's where those numbers come from. 1 degree smaller. And then we'll say plus our remainder 7 over what? Good. X plus 5. We go back to the factor of x plus 5. We only use the root of negative 5 to do the synthetic division process. When we go back to writing it out, we go x plus 5. So here's again. This function here from space, when we zoom way out, looks like this function here. From space, the function on the left looks like that quotient on the right, because 7 over x plus 5 goes to 0 as x goes to infinity. Your remainder will always go to 0 as x gets really, really big. Okay? There you go. So we know how to do long division, and long division works all the time. Like we couldn't have done synthetic division on this one because we're dividing by a quadratic. If you go back to that first one, this is a quadratic. So that means synthetic doesn't work. But if we're dividing ever by a linear factor, I can use synthetic division, and it's just faster. It's cleaner, right? There's fewer moving parts. All right, let's look at synthetic substitution now. Synthetic substitution is essentially synthetic division, but it's in a different context, okay? Let me show you what I mean here. Let's say that I had this polynomial p of x, and let's say I let it equal the dividend of 2x to the fourth plus 9x cubed plus 22x minus 8. Let's say I wanted to evaluate that polynomial at negative 5. So let's say I have the polynomial p of x, which is the dividend. This is our dividend. And I want to evaluate it at negative 5. What would we do to evaluate that at negative 5 without a calculator? What would I do with the negative 5? Well, would I just plug it in for x? It would be 2x to the fourth plus 9x to the third plus 22x minus 8. And what would go inside each of those parentheses? Negative 5. Ooh, would that be fun to evaluate without a calculator? Ooh, what would negative 5 to the fourth power be? 625? Okay, times 2, 1250. And I'd have to write down 1250. And then I'd have to do the next one. Negative 5 cubed, that's negative 125 times 9. That's negative 225. I have to keep track of all that, right? And then I'd have to come back and add those together, right? Yucky, yucky, gross, gross. YYGG. Yucky, yucky, gross, gross. What if I told you that there was another way to evaluate that polynomial at negative 5 without having to do all those large powers and then remembering numbers and adding them together? What if I told you that you can evaluate the function at negative 5 just by keeping it down to two simple things, multiply and add? multiply and add, multiply and add. You'd be interested in that, wouldn't you? Okay, here's how you would evaluate that polynomial at -5. You would take the coefficients of the x's and you would write them out along the top, putting a 0 as a placeholder for anything that's missing. You would then put the -5 out front, which is the x value we're trying to evaluate it at, and you would just go through the process of synthetic substitution. When you get to the end, when you're done with all your multiplying and adding and frolicking through the problem, you would get to the end and you would end up with 7. Well, guess what? 7 is not only the remainder when you divide by x plus 5, this is also p of -5. It serves two purposes. It's fantastic. The 7 is the remainder when you divide by the factor x plus 5, but it's also the function value when you plug in a -5 into the dividend. And wasn't that a lot easier to get the 7? We just brought down the 2 and then we multiply, add, multiply, add, multiply, add. It was easy. Okay? So whenever you're using the synthetic division process to evaluate a function, instead of trying to do the division, it's called synthetic substitution. Okay? It's called synthetic substitution. Let's try it out here. This is example 3. Let's say I have the polynomial 4x cubed plus 3x squared plus 2x. I want to evaluate it at -2. Well, there are two ways to do it. I can say p of -2 is equal to 4 times -2 cubed plus 3 times -2 squared plus 2 times -2. And then I can work down and say that's 4 times -8 plus 3 times 4 minus 4. And then I can say that's -32 plus 12 minus 4. And then that's -20 minus 4, which is -24. Gah! I must have lost 5 pounds doing that. That was a lot of work, wasn't it? I had to raise things to these large powers like cubes and squares, and then I had to keep track of what each term became just so that I can come back at the end and add all the terms together. Is there another way to do that? Yeah, let's try it synthetically. If I'm going to do it synthetically, I'm going to take the coefficients of my function and I'm going to write them in descending order, and I need to make sure I have a placeholder for everything that's missing. So as I start on the left, I'm going to put a 4 for the x cubed, a 3 for the x squared, a 2 for the x, and what's my constant? 0. You need a 0 at the end because there's no constant. You can have a placeholder at the end. All right, now I'm going to draw that line underneath, and I'm going to put that box out front, and I'm going to put the return box on the bottom. And if I'm trying to evaluate the function at -2, guess what I'm going to put out front? -2. Yeah. And let's see what happens here. I bring down the 4, that primes the pump, and then we multiply. What's 4 times -2? -8. I multiply, and I slide it up. Then I add. What's 3 minus 8? -5. What's -2 times -5? 10. What's 10 plus 2? 12. What's -2 times 12? -24. What's -24 plus 0? -24. Hot diggity donut. Is that the same thing we got over there when we did it by the sledgehammer method? The brute force method? It sure is. Which method do you prefer? I prefer the synthetic version. Yeah, the synthetic version. Now, keep this in mind that if I just look at this from a slightly different context, I could also say this. Here's the other context. I could say 4x cubed plus 3x squared plus 2x divided by what? What would be the factor that's my divisor? Not x minus 2, but x plus 2. Right, remember it's always the opposite sign. That's equal to 4x squared minus 5x plus 12 plus the remainder, -24, all over x plus 2. It means the exact same thing. We just look at it from a slightly different context. Now, is x plus 2 a factor of 4x cubed plus 3x plus 2x? Is x plus 2 a factor of that cubic? No, because the remainder is not what? It's not 0, right? If the remainder is 0, the divisor is a factor. The remainder is negative 24. So that means that if you were to look at the graph of P of X, if you were to look at the graph of P of X, the ordered pair negative 2, negative 24 would be on the graph. It would be right there. Okay, here's negative 2, here's negative 24. That cubic polynomial passes through that point. And it's not on the x-axis, is it? So it's not an x-intercept. It's not a root. It's not a 0. Okay? So synthetic division is incredibly useful. I can use it for two different things. I can use it for synthetic division by a linear factor, and I can also use it to evaluate a function at a particular value of x. Okay, we're going to hold off on the remainder theorem and the factor theorem for tomorrow because I think the bell's going to ring soon, isn't it? Yeah. Okay. But you got a good idea of what synthetic division is, and while with the rest of the time, I'll hand back your quizzes.